talk of the program will be given by Tyler Helmuth, who will tell us about continuous symmetry and the arboreal gas.
Okay, so thanks very much for the invitation to speak. The organizers chose to pick a rather ambitious set of topics for the meeting. I think they're all quite difficult. I suppose the thing I know the most about from the list of 3 challenging topics is continuous symmetry. So my hope here is to tell you something about this object called the arboreal gas and why it's related to continuous symmetry. In terms of results, some of you will have seen basically the results about the arboreal gas that I've said before. But I don't just want to entirely reheat the soup, so to speak. So instead, I'm mostly going to talk about continuous symmetry and try and explain why that motivates what we're talking about. Now, in the audience, there are a few people who are, absolute experts in most of the things I'm going to say, and I apologize if I make you a little bored along the way. Hopefully it's okay. And there's a couple people in the audience, 2 of them, who I think this whole talk could be considered an expansion of one single sentence in a paper they posted on the archive a couple weeks ago, Paul and Wei. So the 2 of you will be entirely bored, but hopefully it's okay, so first is going to be about continuous symmetry in a context where that's, I think, easier to see. So I'm going to tell you some things about the ON nonlinear sigma model. So this is a spin system, so we're going to have some finite graph with vertex at lambda. For simplicity, you should probably think about lambda as being some box in ZD, just to make things concrete. The configurations of the spin system are going to be assignments of vectors to every vertex in the graph, so I'll call those U. So UI, you should just think about it as being x1i up to x and I, and it lives in the unit sphere. This is an example of UI in the case of the 2. So formally, just to make everyone comfortable, hopefully, n equals 1 somehow is the Ising model, although this doesn't have a continuous symmetry, so please don't think about this during the talk. Or don't think about it too much. N equals 2 is the rotor or XY model. And n equals 3 is the classical Heisenberg model. Okay, so hopefully some of these names are familiar to you, but if not, you can just think about these spins. I'm going to fix some beta and some h, and I'm always going to let E be this vector pointing in the final coordinate of unit. Okay, so I want to describe a spin model, so I have to tell you how the spins interact. And they're going to interact in the way you would probably guess. So I look at the gradient of the spins on adjacent sites I and j. So I and j is an edge in the graph I'm considering. I look at ui minus uj dot ui minus uj. And this won't really play a big role, but conceivably I'll mention it. So I could also put some external field, h, pointing in the direction 0, 0, 1. And I have each spin interact with that external field. So given this, there's some graph fixed in the background, finite graph. The expectation of some function of my whole spin field is proportional to integrating f of u e to the minus h. And the integral is with respect to product surface measure on the sphere. So this is So if the gradient is big, I'm giving you a penalty, so the system is trying to make the gradient as small as possible. And if there's an external field, everything is biased pointing in the direction of the external field. So a trivial but important remark is that this is what makes it not Gaussian. I've restricted the spins to live in a nonlinear space, so it's not a Gaussian model, and that's the whole challenge. And obviously this has a continuous symmetry because the sphere can be rotated around at least when h equals 0. Okay. So this is a good point at which if the model's not clear, you should interrupt me, and you should interrupt me at any time. So the beginning, like this is precise mathematics, and what I'll tell you next are some results, and those are known results, theorems. And then the next part will be considerably more heuristic. So especially in that part, interrupt me if something's not clear. The goal is that it's understandable. If, because it's a heuristic discussion, we should do it afterwards, we can talk afterwards. So I'm going to tell you some basic facts about what happens for the ON spin model on ZD, and I'm going to tell you facts about this correlation function, the inner product of the spin at some chosen origin and some vertex x, and I'll think about them as being far away. And basic is in quotes because some of these things are fantastic theorems. The first thing is not so difficult though. If beta is small, so you're at high temperature, then there is exponential decay of this 2-point correlation function. So if beta is very small, this bias for the gradients is not very large, and you should look a lot like a product measure, and indeed you do. So this is, let's say, not so hard. For example, you could use the random walk representation. We see dimension starting to play a role for the next basic fact. So if D is at least 3, and beta is large, so this is low temperature, beta is inverse temperature. So there is an ordered phase. Meaning there's no decay at this 2-point. So at very large separations of 0 and x, this 2-point function converges to a constant that's positive. So even over arbitrarily long spatial separation, they basically point in the same direction. So this is the analog of the phase transition for the Ising model, which is maybe more familiar to some of you. That already happens in 2 dimensions. Here you have to wait until 3. And, basic is in quotes, of course, because this is quite an amazing result of Froelich, Simon, Spencer. Yes?
And this is for any age?
No, so h, this is for h equals 0, that there's no decay. So here, h equals 0. So this is a basic fact, but in fact we don't even understand this basic fact all that well because the proof relies on reflection positivity, and if you took next, nearest neighbor interactions, for example, we wouldn't know how to prove this. So let's scratch out. Okay, so if you view the point of talks as collecting interesting open problems, please prove this when it's next, nearest neighbor interactions. That would be fantastic. So maybe let me just say, for all of them, I should probably put each equals. Okay, so that's in 3 dimensions. What about 2? So in 1 dimension, it's a one-dimensional nearest neighbor statistical mechanics model. There's never any phase transition, so I'm not going to talk about it. 2 dimensions, interesting. It's a basic fact that no ordering transition is possible. So for any inverse temperature, there is some positive constant such that this correlation function decays, at least polynomially fast. So again, this is, a significant theorem. Usually it's called the Merman-Wagner theorem. This particular form, in this case, is McBride's theorem. So in 2 dimensions, there won't be a phase transition in the sense of the spins pointing in the same direction. This doesn't say there can't be any transition of any sort, but first maybe let's see why this theorem is intuitively true. And it's enough to consider just n equals 2. So what you do to think about this is you suppose that the system does order in some direction. Maybe you pick some boundary condition, like all the spins point to 0 in terms of angle. Then everywhere else, if they order, you should see something quite close to that. And then you have an interaction just of the fluctuations delta ui from the fixed chosen direction you order in. So when I look in the action, ui minus uj, all I see is delta ui minus delta uj. And these fluctuations they more or less live in the tangent plane to the point that I ordered. Right? This deviation is essentially just pointing in one direction in the case of n equals 2. So one way to interpret that is that at least heuristically, the n minus 1 directions in the tangent plane, if I'm talking about the ON model, are an n minus 1 component Gaussian free field, or they should be very close to that. So this is if ordering happens, then this is reasonable, but that's a contradiction. So why is that a contradiction? Well, what's the variance of the Gaussian free field? It's blowing up as I take the box to the whole plane. So if I think about taking a finite box. The variance is not finite, but the variance is supposed to be a Gaussian free field. It's supposed to be a small fluctuation. And if the small fluctuation has infinite size, well, it's not a small fluctuation. It means that the thing you started with was nonsense. So it's this part. If ordering happens, that was nonsense. Okay? So that's intuition. In fact, the proof is not so much longer than that. Maybe the same number of lines. But let's just go with the intuition for now. To get this polynomial rate is also a short argument, but okay, so what actually happens? We just said ordering can't happen, but that's not the whole story. So if n equals 2, so it's this model, taking values in the circle, then polynomial decay is correct. So that's a theorem of Froelich and Spencer. This is the famous BKT transition. And what's really interesting, if n is 3 or larger, it's open what actually happens. So there are conjectures about this, and I'll come to that in a second. But already when BKT, or at least KT, Kosterlitz and Thales, when they predicted that this polynomial decay happens, they already said, we don't think it will happen for 3 and higher dimensions. They didn't think there would be polynomial decay. So the truth here is supposed to be that its polynomial is not correct. It should always be exponential decay. We'll come to it. Okay, so this picture that you look in some direction, you order in, and things fluctuate around it like a Gaussian is sometimes called the spin wave picture. And now that I've said this, the single sentence I'll be explaining from a paper of Paul and Wei is that the arboreal gas is an example where you can verify the spin wave picture. So if you want to know more about the spin wave picture, you should look at this paper of Paul and Wei that was on the archive a few days ago. They have some recent progress on the Villain approximation to the O2 model, but they also sort of summarize other things that are known about it and give you a good way to see what that literature is like if you want to. Okay. I should say I've given a very short selection of results compared to what is known here. Happy to tell you about other things. Okay, so now I want to go to something that's going to be more heuristic because we don't know how to prove anything. So that's what happens in d equals 2 when n is at least 3.
In that intuition, where are you using the 2-dimensional?
So the variance blows up. Yeah. Okay, so I want to tell you about n at least 3, but I don't want to write long formulas. So I'm always going to write formulas as if n equals 3. So then I can call the components x, y, and z, because that's the standard thing to do when you have a vector in R3. But then when it's important, I'll restore the capital N, so you can see what the formula is supposed to look like in general. Okay. So what I'm doing here is I'm going to explain in a less sophisticated way arguments given by Polyakov for what happens when n is at least 3. Or I'll explain a small amount of what he says. And the starting point is something that seems absurd given what I just told you, which is that you suppose the field actually sort of orders in some direction, even though we just said that won't happen. So what you should have in mind is that you take beta enormous and you only look over relatively short scales, where then still locally you will be ordered in some sense. There are more sophisticated ways to formalize that, but let's just take the simplest one. So just pretend the spins roughly look like they're pointing in the z direction. So then, instead of dealing with these spins living on the sphere, I can just choose some explicit coordinates. So z is a function of x and y, and because everything points in the z direction more or less, this should be just square root 1 minus x squared plus y squared. And I want to make things nice, so I'm going to say phi is equal to, 1 over root beta. Phi is equal to x phi. Okay, so I'm going to make the change of variables that x and y are replaced by 1 over root beta, some 2-component vector phi. So this is 1 minus phi dot phi. Okay, and if I do that, so to symbolize that the things are getting less precise, I'm going to start writing these approximations. Well, the x components still interact with the gradient. So this is xi minus xj squared plus yi minus yj squared. And then I also have the z part, which is basically 1 over 2 beta. The inner product of the gradient of phi squared. So this is zi minus zj squared, the leading order in 1 over beta by expanding the square root. There's also another important term, which was the thing that made this non-Gaussian, which was the measure. So there's also a term from the measure. So the measure is just 1 over z when you choose these coordinates. That's just multivariate calculus. So you get another term, minus log z in the exponential if I want to put everything in the exponential. And this is basically 1 over 2 beta phi dot log, just by expanding the log to the first term. So I'm only keeping leading order terms, and this is something that's, of course, profoundly incorrect. Phi was supposed to be the x and y coordinates of something that lives in the sphere. So there's a strong constraint on what they can be, and now I've said, well, I'm going to completely ignore that and just, the log would make no sense once phi is too far away. But if beta is very large and phi doesn't move so much, maybe it's okay. But clearly, if phi gets big, there's a problem. So if you want, this is...
So that phi 2 is the square, the Euclidean square, not the 2 component, right?
That phi is phi dot phi. So this is... Okay, so this is, if you like, one way to make this spin wave picture precise, or maybe not precise, but sets the goal for you more clearly. It's, you have a Gaussian part, you have a very small fluctuation away from being Gaussian from this first term, and you also have a fluctuation away from being Gaussian from this term in the measure, and can you control them? And that's a hard task in general, in 3 dimensions already. In some sense, though, this is where predictions for what happens for n at least 3 come from. So you define a new expectation. So I use my local coordinates. So I say, well, I just have some perturbation V that's defined by these 2 terms of the Gaussian part of the measure. Okay, so V is just defined to be the thing that I get from this approximation, and I won't have my original model, but I'll have something that's possibly close. And here, it's the Gaussian free field with n minus 1 components. Because well, that's how many components phi has. Okay. So, not exactly this way, by something slightly more sophisticated, Polyakov then said, okay, I have this formula, I should use the technique of the renormalization group, and it will tell me what's going to happen. Obviously, I don't have time to explain the whole renormalization group here, so what's the basic idea? So my Gaussian free field has some covariance C, and I'm going to integrate out this covariance in multiple steps. So this is just a fact about Gaussian expectations. If you can write the covariance as a sum, you can think about a convolution of Gaussian integrals. A more familiar setting would be add up two independent Gaussians to get a Gaussian. Okay, so this is just a fact, and the idea of the renormalization group is to use this fact to compute complicated integrals, or that's the zeroth order idea of the renormalization group. So what should you do? You should do this, and you should choose C1 to be the correlations over short distances. Place where the assumption that beta is really large, so you're locally ordered, sort of makes sense, and I should be able to exploit I should be able to exploit or make use of this decomposition of the covariance. Okay, I'm not going to do the computations. I'm just going to tell you what Polyakov found. So the good thing here is that you're computing or approximating the expectation of this potential V with respect to a Gaussian measure, but beta is huge, so you might trust what happens if you sort of just expand the potential as a power series, do Gaussian computations and rearrange things. So when you do that, what you find, a new potential for the remaining expectation that you have to compute. And the miracle, or in this case, just cheating because I'm not showing you anything and not proving anything about errors, is that the new potential that you get looks like the old one, but with a change of the temperature. So just a new beta tilde. And up to some numerical factor, what you find is that the new beta tilde is beta minus n minus 2 over 2 pi. So what does this say? This says that if I integrate out what happens over short scales, so then I have a theory of what's happening at a larger scale, I see something with a higher temperature. So this suggests that I'm not going to have any order. Well, it decreases if n is at least 3. If n is 2, this says nothing is changing. But if n is at least 3, then temperature is getting higher. So I should be getting closer to something with rapid decay of correlation. So this is a somewhat grotesque injustice to how Polyakov argued this, but this is the idea. Okay. So it suggests n is at least 3.
So in terms of your original V beta,
Yeah.
are you saying that when you go to large scales, the massive term there is going to dominate the other one?
Right, so I'm saying the approximation I made is getting worse.
Okay.
Because I was saying if beta is huge, this is a small perturbation, but actually it's getting bigger, so that's not such a good situation. Right, so this suggests this exponential decay, which is Polyakov's conjecture, sometimes what people say. But actually Polyakov is a little more circumspect about it if you read what he writes. He says, this is not so clear, although something closely related is quite clear, and I want to tell you what that is, and then hopefully I'm not out of time and I can still mention the Arboreal.
If I understood your question correctly, I don't think it's saying that massive term, the V beta, is becoming dominant. It's much more subtle, but because the mass is not 1 over beta, it's e to the minus.
Yeah, so we'll come to
if
what the mass is.
I see. Okay.
But it's certainly not becoming a small perturbation anymore, is the issue.
So in high dimension, you see a fixed point. high dimension, you have d minus 2 in front of beta, maybe?
This is a two-dimensional calculation,
but
so this is not correct.
I guess you can do the same thing for high dimension.
Yes, yes, yes. Yeah, but for now, let's just focus on that. Okay, so it suggests exponential decay at large distances, but in fact, what this really tells you something about more convincingly, and this Polyakov has no doubts about, and it's fairly convincing, is that you should take a unit torus and try and construct some continuum limit. So that means you should consider a sequence of finer and finer mesh approximations where x and y are held fixed on a macroscopic distance. And if you want to construct an interesting limit here, the goal, interesting here means not Gaussian. So you would like at the very end that this perturbation term actually has an effect. But it can be really small, that's okay. So the good news is that that perturbation effect is getting bigger as you go to larger distances. So it means that you could have made it astonishingly tiny at the beginning, and you just need to control it until the end, and it can even be small at the end. So this can be a small parameter in your whole analysis as you change scales. What I mean is that you fix So you're going to approximate the continuum torus by some torus with mesh size L to the minus k, which I'll call lambda k. K is big. And you want to study the k to infinity limit. And this is basically what Polyakov says. I'm writing it a little imprecisely, but, well, actually quite imprecisely. So when you want to solve this problem, you should let beta depend on k. The only goal is to construct an interesting continuum theory, and you don't have to fix beta for anything. And the way you should choose it is like some large constant beta bar plus n minus 2 over 2 pi log L to the k plus some log term. And I could be more precise about the coefficient here, but from the point of view of the talk, it's not important. Then, if I look at the 2-point function, with temperature beta k, take k to infinity, so I should recenter. And rescale correctly. Then this converges to some function g beta bar x. And as you take x small, this looks like it's blowing up like log 1 over x to the n minus 1 over n minus 2. As x goes to 0. So you should think you fix 0 and x, you take the mesh size to 0, so now you have a continuum theory, and then you pull 0 and x together and you see this singularity, and it's like a power of log that depends on n. This conjecture, based on what Polyakov explains, is still at the level of theoretical physics. But it's quite convincing. The reason being that along the whole argument you have a small parameter, so you at least have some hope of doing this by some perturbative control. So this is sometimes what's called asymptotic freedom. with the idea being that as you go to shorter and shorter scales, so closer to the beginning, the perturbation is getting smaller and smaller. This is not the only meaning of asymptotic freedom in the physics literature, but that's what's meant in this context. Okay. The thing that's usually called Polyakov's conjecture, which is that you fix beta and look at 0 and x well separated on the infinite lattice, seems much harder. To give you some idea, and maybe this explains what Roland was saying a moment ago. So to get the continuum limit, so to get a continuum limit that has interesting correlations, you need the correlation length to be like the inverse of the spacing between lattice points. Otherwise, there's no way these two macroscopically separated points will interact. And if you just check that this is consistent with the idea that beta should scale with k in the same way, so what I'm doing is taking the fixed lattice problem, supposing there is a correlation length, and then you plug in the formula beta of k into it and ask that the answer is 1 over epsilon. It says that the correlation length should be e to the 2 pi beta over n minus 2. So this says that it's much more subtle than one term kicks in, because actually, if you can actually analyze it in detail, you should find this very surprising, enormous correlation. This is the kind of thing that you can't possibly simulate on a computer, although people have tried to some extent. But you'll never be particularly convinced about a simulation when you have to detect a length like this. Okay. So another way to put it would be that if you want to study the mass gap, you should take the continuum limit, and then you should let the torus size get big. Otherwise, you can't even ask about what happens at large separations. So to do that, you would need a construction that's uniform in the volume of the torus. And this conjecture says nothing about being uniform in the volume of the torus. Okay. So I have like 10 minutes, 12 minutes, something like that?
Something like that. I think so. He started at 20 and talks at 50 minutes, is that correct?
Okay. Good, so then this is what I wanted to say about continuous symmetry, and in some sense, you know, maybe the dream audience for this was myself 5 years ago to understand what was happening better. But in fact, this is motivation for various works on the arboreal gas, and including ongoing work that I won't really talk about. But let me tell you what that is and why it's related. Okay, so I'm going to tell you an alternate history of how people could have decided to study the arboreal gas. It's a lie, but suppose you do all of this and you wanted to check that it's true and understand what's happening with continuous symmetries. What you could ask is, well, maybe I can invent a model where all of the ways I cheated before are actually exactly correct. Okay. Of course, there's no reason that such a model should exist, but it does. There's a small price to pay, which is that it has this somewhat intimidating name, H02 model, which is not one of the standard models we well, I don't know when you hear about it, really. Certainly not as an undergrad, or most likely not as a graduate student. So that's one miracle. This actually, if you had this desire in an alternate timeline, you could actually achieve it. There's a second miracle, which is that not only does this exist, there's a very simple and totally different description of what it is, or what some aspects of it are. And that's where the name arboreal gas comes from. So let me tell you that, because it's easier than telling you what H02 is. Okay, so this is sort of a I think the fact that it exists could already be called a miracle, so this is the second miracle. So whatever this model is, if I compute the analog of the two-point function, the spin-spin correlation, up to a minus sign, it has a very simple description. It's a connection probability. In the combinatorial model of beta uniform random forms. So just to be sure that that is something that makes sense, it's just this ratio. When I sum over all forest subgraphs of a given graph, so maybe my graph so a forest subgraph just means no cycle. So this is a forest. It's a not particularly interesting one, but it is. And I have 1, 2, 3, 4 edges, so this would have weight proportional to beta to the 4. And if this was 0 and this was x, then this indicator would be satisfied. 0 and x are in the same tree in the forest.
Can I?
Yep.
So when you say, just quickly going back to the H02 thing, when you say all the squiggles were equal
Yes.
sign, does that mean that you can prove everything that followed from the squiggles in the?
Not everything, but many of the things, so that's what I'll say next. So this fact, I should say, is really a reinterpretation of something discovered by Cracciolo, Jacobson, Solur, Sportiello, and Sokol, to get them in correct alphabetical order. They thought about it slightly differently, but it's the same idea. So first, let me sort of say what Ellen just said, which is that all of the physics predictions carry over, but you have to do a little twist. So everywhere I saw a 1, because there was a component of the free field, now I should put a -1, because my commuting variables have become anti-commuting, and this is the way the computations work out. And also beta should go to minus beta, because somehow this is a hyperbolic model, so there's been a change of the inner product. So So if you want to make these predictions work, you should take n to be -1 and beta to minus beta. And if you check for the two-dimensional discussion of n greater than or equal to 3, it means that beta is still behaving in the same way in 2 dimensions. Temperature is increasing at larger scales. The n equals -1 is because for the ON model, we had n minus 1 components of the Gaussian free field. And in this model, the H02 means that there would be 2 anti-commuting free field components. So n minus 1 has to equal -2, which is n equals. Okay, so how much you believe this prediction, a little unclear. So maybe I'll just end by saying 2 theorems. So the first was with Roland and Nick Crawford and Andrew Swan. In dimension 2, there is polynomial decay. So that's just like the Merman-Wagner theorem. And with Roland and Nick. And so I haven't been very precise at any point really in the talk, but this definition of the forest model only makes sense in finite volume. And taking infinite volume limits for the forest model is actually not so simple. So what I mean is that we have this estimate uniform in the volume. In dimension 3, we have to work on tori. But maybe one way to summarize it is to say the spin wave picture is correct. So if beta is large enough, so up to some error terms, what you see is a constant term that close to 1 as beta gets large. So this says that there is an ordering transition because distant points are supposed to be in the same tree with high probability. And the correction looks like a Gaussian fluctuation. Okay. Yes?
Is it easy to see what is the symmetry here?
Well, it's the symmetry of this space.
Okay.
So the sequence that I'll tell you to get there, which won't quite answer your question, will give you some idea, is that you should think when we were talking about the Heisenberg model, it's the symmetries of this equation, things that preserve this quadratic form. Let me go there in 2 steps. If you look at the hyperbolic plane, it's this equation. Okay. You should look at C positive. And H02, well, somehow you want things to be anti-commuting, so the Euclidean inner product is not such a good idea, because if I squared an anti-commuting variable, I would get 0. So it changes to the symplectic inner product. So what you get is -2. And this is something that has appeared in algebra before. This is OSP12. I don't know if that's enlightening in the moment, but this is the sequence. This is the defining equation for this space. Okay, so in 3 and more dimensions, like I said, we can check the spin wave picture. In fact, even if you look at these things like the parallel spin correlation, we get exactly what you expect. So you really do confirm the whole picture. In 2 dimensions, we can show Merman-Wagner, but of course, that's not the most interesting thing. If you plug in n equals -1 and beta to minus beta, you see that you should have this exponential decay phenomena. That's still open. So maybe to conclude, let me just say that there's still so much that isn't known about this, and it somehow seems like a much simpler setting than the ON model. It has a combinatorial description, which is somehow a shadow of the fact that it's in terms of anti-commuting variables. This removes all sorts of problems that you face in the case of the ON model. So it would be really interesting to have other methods or views about how to analyze this problem. And the other thing is that the spin wave picture actually has a realization in terms of the forests themselves. So in the low temperature phase of the forest, there's a giant tree, but the ones that aren't giant, at least conjecturally in ZD, are still quite large, polynomial size in the volume. Does that actually happen for the ON model, where the spin wave picture exists? You would expect it to be dependent on the representation you choose, but it would be interesting to find a representation for, say, the O2 model, where you also see the spin wave realized combinatorially in some sense. Okay, thanks a lot.